Okay. Good evening, everyone. This is Celso Battaglia, Astro 10 online class, and today I should continue exploring the sun. But yesterday I speed up a little bit and I cover most of the main topics related to the sun. I didn't get a lot of input with respect to specific issues on the solar atmosphere and solar interior. The discussion that is going on now has to do with the topic of next week, which I intend to initiate it today, which is stellar evolution. The discussion I'm having some students not clearly defining all the steps in stellar evolution, and I'm trying to provide a feedback so you can go back to your text and try to fix it. So closing with respect to the sun and also with respect to the exams we had. So yesterday we closed midterm number 2 and we have a midterm number 3 coming up next week. And I will let you know when the exam is going to be open. So you can make your first attempt. So there will be, as it happened with the previous exams, there will be a second attempt 2 days later, not necessarily the same questions, but it's a second attempt, and I pick up and I choose the highest score of both attempts. What we are discussing now is stellar evolution, and I gave you a series of keywords, and you have to write a composition including all keywords that has to do with the process of stellar evolution. One of the myths some people developed is the myth that somehow stars initiated their lives with a big boom, with a big expansion or display of light and energy, like babies, right? So babies had tons of energy. They don't stop. They are non-stoppable creatures. And what we learn in chapter 5 first, and then 2 chapters ago, is that gravity is a slow process of star formation. So in our galaxy, there are several in fact, thousands of what we call giant molecular clouds. They are thousands of light years in extent. And these giant molecular clouds, they, in specific locales or regions, the concentration of material is good enough to initiate a slow process of contraction. And when this contraction initiates, the gas becomes packed. And then as the gas becomes more packed, especially in the center part of this course, more collision will take place among the molecules that make up this gas. And as collision takes place, the temperature rises up. And when the temperature rises up, the pressure also grows. And that halts, and that's kind of works as a brake to the process of slow contraction the stars undergo before they become what we call stars. So let me recap all of this. So the gas in the interstellar medium, or the gas in these giant molecular clouds, it's a cold gas and very thin. The density of this gas can't compare with the density of our atmosphere. Our atmosphere is rock solid compared with this interstellar gas medium. It's very thin. You have one atom or so of hydrogen in few cubic meters, so it's almost nothing. It's almost a perfect vacuum. You cannot create a vacuum on Earth that can match the gas or the density of the gas in the interstellar medium. But yet, with all this low density, in some regions, it is good enough for gravity to start accumulating the gas and initiating a slow process of contraction. So basically, contrary to what some people might think, when a star starts its life, it's not a major fire rock, uh, firecracks of explosive displays of light. On the contrary, it is a cold gas that is not luminous at all. There is no radiation, optical radiation we can see coming out of this system, but eventually it contracts, heats up, and then eventually light um, can escape. Optical light can escape out of the center part of these clouds. Now, as I mentioned, once this core becomes hot enough, it is surrounded by remaining material that initiates the contraction. So for an observer outside, he or she will not see that light coming through, because that light that is produced in the core, that is going to be the place of a new star, that light is trapped by the gas itself, and it does not escape. But as the process of contraction speeds up, as our book well rephrases, is a process that comes from inside out. So eventually, the amount of radiation is good enough to break through this shell, and then outside observers can see it. And then we call that a protostar. Protostar. And eventually, this protostar will be host a center core that is dense and hot enough to ignite fusion reactions, hydrogen into helium, as we saw yesterday as one of the sources of energy our sun has. Just a recap of what we saw yesterday, the sun's core, the sun's central part, is the powerhouse, is where sun's energy is being produced, and that is the result of fusion reactions of hydrogen, 4 atoms of hydrogen in 1 atom of helium, plus gamma rays that by diffusion help to keep the sun stable, and neutrinos readily escape the sun. So in this chapter, which we officially start on Monday, and I'm trying to speed up now. Tomorrow we don't have chat room. So basically, the element, and this is important. This is very important. The element, or the aspect of what speeds up stellar evolution. So the quantity that is responsible for controlling and guiding stellar evolution, which means which makes more efficient, faster, or slow, that property is the material. So high mass stars that are more massive than about 8 times the mass of our sun, they undergo evolution very fast. Whereas stars, there are low mass stars. They are called as low mass stars. They are stars that have much less mass content than 8 solar mass. For instance, our sun is a typical low mass star. Most of the stars in the galaxies are less massive than the sun. When Mother Nature initiates star formation in our galaxy, she prefers, or it prefers, or he prefers, whoever you want to address it, Mother Nature, Mother Gaia, it prefers formation of low mass stars, subsolar young stars. And what we learn is, in this chapter, is low mass stars, they go through their evolutionary stage very slowly. Just to give an example, a star like our sun will complete all its evolutionary sequence in about 10 billion years. The sun is right now half of its evolutionary cycle. It's about 4.5 billion years of age, has another 4.5 or 5 billion years to go. but eventually its life cycle will be completed, and which comes to terms that everything in the universe had a beginning, has a process of maturation, and then eventually it faces its demise. It's pretty much, complete its life cycle. So stars, what you could stop and think, why stars undergo life cycle? Why do we care for it? Well, answer to this question we learn in chapter 1. If you look around yourself, we have water in our body. That water has hydrogen. Hydrogen is an atom that was manufactured in the Big Bang. The very 3 minutes in the life of our universe, hydrogen and helium were formed, were created in this cosmological nucleosynthesis. But all the other atoms couldn't be formed in the Big Bang. It was required that the stars came alive, and the very first generation of stars were stars of hydrogen and helium only, because that was the gas available. So once these stars initiate their evolutionary sequence, and the end of their evolutionary sequence met the formation and creation of atoms, freshly formed atoms that were then released to the interstellar medium. So take a look now and touch anything in front of you. It might have carbon, like our body. It has iron, like our body, our blood. You might have metals all around yourself. You might have magnesium, zinc, zirconium, rubidium, gold. I mean, all these atoms were formed in a brief amount of time in a process we call nucleosynthesis, stellar nucleosynthesis. And all these heavy atoms were formed when the massive stars exploded in what we call supernova. And as a result of this explosion, again, in a very short amount of time, these atoms were formed and then spread over the interstellar medium. And then new generation of stars came by, right? The process is initiated again. Gravity kicks in, pull the gas together, but now the gas has metals. Metals that were formed by stars that no longer exist. They are gone. And then we have a second generation of stars that undergo their own evolutionary cycle. They die and then explode and then spread over these newly formed metals and atoms in the interstellar medium, which will favors and facilitate formation of a new star. So just to make a short story, as the galaxies evolve, as the time passes by, the universe or our galaxy becomes more metal rich. Our galaxy becomes of less hydrogen, if you will, and more of the metals as a result of stars. We could not be here if it were not for stars that no longer exist. I mean, our biochemistry depends on these little atoms, right? Magnesium, potassium, calcium, sodium, and they were all formed in stars. And our sun is processing and undergoing exactly this process right now. So let me go through the PowerPoints quickly. So stars are constantly radiating energy by hydrogen to helium in their core. We saw that. And definition of low mass star has less than 8 times the mass of our sun. We identify stars based on their surface temperature, and because of the spectral classification we studied in chapter 4, if I'm not mistaken, stars can be classified from O, B, A, F, G, K, M, and there is this mnemonic sequence you can try to memorize. O, be a fine girl or guy, kiss me, depending on what you like. So O stars are very hot and huge, and M stars are very cold and small. So you go from hot members or hot type of stars to cool type of stars. And if you think about stars that are those um, subjected to fusion to host fusion reactions in their very core, all stars are the most massive stars available um, in our galaxy or in the universe right now. Stars that are very massive, 100 solar mass or so, they are not stable. They break apart. So all stars, 40 solar mass, and then you go down in mass content up to M5, which is the coolest in this table, which is only 20% of the solar mass, just to get an idea. So in terms of stars or black body, big means luminous. If you are big, you are luminous. You have a large surface area that can produce light and emit light. So if you look at all stars, they are 500 times as luminous as the sun. In this scale, the sun has one factor of luminosity, right? So the sun is one. So an O star is 500 times as luminous as the sun. If you think about energy, an O star can, per second, every second, can send out 500 times more energy than the sun does. And then you go down in the scale up to an M star, or let's look at a K star. A K star is about 10-20% of the solar luminosity. So the amount of energy is not that great. Now, if you knock on the door of physicists and astronomers, they would tell you that based on what they know about the behavior of gas and the behavior of nuclear reactions under certain pressures, and because they can calculate the range of pressures from the solar or the star surface all the way to the core, they can tell you how long it will take for a certain content of hydrogen and helium being converted into heavier atoms as a result of fusion reactions, like carbon, neon, magnesium, and so on, so on, so on, oxygen. And then when they calculate this time, it allows us to infer the age of a star. So how long a star will exist in our universe as a main sequence star, as a normal star. So and these calculations are such that an O star, which is big, luminous, and very massive, 40 times the mass of the sun, they will be behaving as a main sequence for as much as 800,000 years. 800,000 years. Now, in the universe, probably in my lifetime, 800,000 is a long time. But in the universe, 800,000 is nothing. It's a snap in the finger. Now, look at the sun. The sun, in the main sequence, is going to be behaving or living the way it is for as much as 10 billion years. 10 billion years. So basically, if you think about the main sequence, the sun is going to be pretty much the sun for a good another 5 billion years. So the sun is in the middle of its life cycle. And a star that is a K5, it's going to be for 40 billion years. And an M5, by the way, 40 billion years. 40 billion years is more than the age of the universe, right? The universe is 13 billion years of age. So 40 billion years, these K2 stars have not completed their, no K2 star in the universe have completed their life cycle, because they complete their life cycle in a time that is bigger than the age of the universe. So they are still undergoing their normal evolution. So mass established the stellar evolutionary track. And that is what this diagram attempts to indicate. So we have a diagram that gives you in the y-axis the amount of energy the star is sending. We call that luminosity. And if you look in the horizontal axis, we have surface temperature, right? And the surface temperature is such that to the left-hand side is where the hottest stars should be, and to the right-hand side is where the coolest star should be. And these tracks that you see in this diagram are the so-called evolutionary track. This evolutionary track is the result of modeling, basically. Again, physicists and astronomers, they know the size of the star. They can determine the volume of that star using different techniques. They can, if the star is a member of a binary system, they can determine the mass or the density ratio between those two stars. And by knowing and have access to that information, as well as surface temperature, astronomers can predict the behavior of the gas that is inside the star. It's pretty much basic physics we learn in the college, in the university. And by doing so, by comparing the interplay between gravity that is slowly contracts the star and the heating up of the star nucleus as a result of making more and more compact and forcing the molecules and atoms into constant collision. And more collision that is, more higher the temperature of the gas will be. And then astronomers and physicists can predict those tracks. So what those tracks, they have a specific name for it. And the name is pre-main sequence track. Pre-main sequence tracks are tracks that indicate the evolutionary sequence of stars before they reach this stage in their lives we call a stable stage, in which they initiate fusion reactions in their very core. So pre-main sequence stars are the stars that are still contracting. They don't have hydrostatic equilibrium established for a long time yet. They are shrinking. They are reducing their volume. It takes millions of years for them to reach the main sequence, but again, millions of years is a short time in the cosmic scale. In our scale is a long time, but it's a slow contracting process that leads to form a star. And then we have pretty much what's called a protostar, right? So a protostar initiates its life, and we barely can see it. It's pretty much surrounded by the parent cloud, right? Is surrounded by the material that allowed the star itself to be formed. But eventually, this material will be cast out. The star from within will shine, will create its own stellar wind, and then eventually this external shell will be dissipated, and then it's not going to be visible anymore. Okay. I didn't want to advance much today. I just want to initiate this subject on stellar evolution because it's part of the discussion, and I know that some of you are having a hard time to. Some students are calling the cloud that formed the star planetary nebula. It's not. The planetary nebula is a stage that occurs when the star itself finishes up its internal fuel and initiate a phase we call Posman sequence phase. Okay, Posman sequence phase. So today I would like to concentrate in those stages that lead to star formation, that lead to the star to become a main sequence called pre-main sequence phase. So we have a process of shrinking. So eventually the star becomes stable, like our sun. And then after so many millions or billions of years, depending on the mass of the star, this core of hydrogen will be exhausted. The fuel of the star will be gone, and then the star will undergo changes, which I will explore on Monday. And these changes will lead the star into a slow process of expansion, and the star will then become become what we call giant star, or depending on the mass, it's going to be a supergiant. Okay. Uh, Again, email me if you have any question, and I will stop taping right now.